This video is the first in a series of videos that are all about trigonometry. You'll find that trigonometry is the study of triangles. But in this video, we'll start off by looking at angles and circles. We'll define angle measure and take a close look at the unit circle. We'll start off a simple definition. A radian is the ratio of the arc length of a circle to its radius. A radian is a measure of span or angle, just like the degree. However, you'll find that the radian has some added benefits that a degree doesn't have. So if we pick 3 points, one at the center of the circle and 2 on the edge of the circle, you see that traces out an angle. The radian measures the span similar to the way a degree does. So we think about this opening as the span of this angle. To calculate the number of radians of this angle, what we first have to know is the arc length. So that would be this distance here. Sometimes the letter that we use for arc length is the letter S. And then we'd also need to know the radius of the circle. I call that R. So the radian, which I might use the Greek letter theta, the angle is simply S over R. One thing we'll need to do is get used to this new measurement of span. One way to do that is to answer this question of how big is 1 radian? Just like you may have been used to measuring length using inches or feet and had to grow accustomed to using centimeters and the knowledge that there were 2.54 centimeters in every inch, we can do the same thing with radians and degrees. So since a radian by definition is the arc length over the radius, 1 radian, exactly 1 radian, is when the arc length and the radius are equal. So I can picture that like this. If I took a rope that was exactly 1 radius long and laid it across the circle like this, that span that would open up right in here, that would be 1 radian. And you might guess that that looks like it's about 60 degrees. And you'd be right. However, we'll soon see that it's not exactly 60 degrees. And we can be a little more exact in the size of 1 radian. In order to be exact with that question of how many degrees are there in 1 radian, we might ask a different question. How many radians are in 1 complete revolution all the way around the circle? So here we go again. Imagine you had a length of string exactly 1 radius long and you were to lay it right here on the perimeter of the circle. That would trace out 1 radian. And then if you did it again, you get a 2nd radian. And again, with a piece of string the exact same distance long, there would be a 3rd. So the angle that would be formed from this point right here at the center of the circle to this point on its right side to this point where the 3rd radian ended, that would be 3 radians. And you notice that it's pretty close to half a circle. If I continue with this process going around, here's a 4th radian and a 5th radian. And you'll notice that 1 more radian, a 6th radian, takes you almost all the way around, but not quite, particularly if you're being very precise with your length of string. There's a good reason for that. We know that a radian is equal to our arc length divided by the radius. If we think about our arc length as being the full circumference of the circle, 1 complete revolution, what we find out, since the circumference of a circle is 2 pi r, we find out that the number of radians in one complete revolution is 2 pi. And of course, since pi is 3.14 and so on, 2 pi is about 6.28. And that's exactly why I fell about just a little bit short with my 6 lengths of string wrapping around that circle. This is a very important result because we now know that one revolution is the same as 2 pi radians. And that's the same as 360 degrees. And that allows us to have a conversion between radians and degrees. There are 2 pi radians for every 360 degrees. Or if I wish to simplify that a bit, pi radians for every 180 degrees. Just like there's 2.54 centimeters in every inch, I can use this conversion factor to switch angle measurement back and forth between radians and degrees. Before we do some practice with that, changing from radians to degrees and back, I want to point out the big idea here. The radian is a measure of angle or span just like the degree. However, it has an added benefit. Since the radian is S over R, where S is arc length and R is radius. Arc length and radius are just both measures of length. Suppose your arc length was measured in centimeters and your radius was also measured in centimeters. That means the ratio that you get there, the number of radians that spanned on that particular angle, it's a unitless measurement. Centimeters divided by centimeters would create a unitless measurement. And this is a key point that makes the radian a preferred measure of angle for mathematicians over degrees. We'll look at a few examples. In letter A, I'll convert 90 degrees to radians. In order to do that, I'll simply multiply by our conversion factor. There are pi radians in every 180 degrees. That gives me 90 pi over 180, or pi over 2 radians. 90 degrees and pi over 2 radians are equivalent. In letter B, do more of the same. 240 degrees converted to radians, multiply by pi over 180. I get 240 pi over 180. We should always simplify with these because it might make the radian measurements that we end up with a little more familiar. We get 24 pi over 18, which is the same as 12 pi over 9, or 4 pi over 3. Try letter C on your own. Pause the video and see what you get. For 315 degrees converted to radians, you should get 7 pi over 4. If not, go back and check that you reduced the fraction completely. In this example, we'll work in the other direction, converting each radian measure to degrees. For letter A, perhaps you remember from our last example that pi over 2 radians was equivalent to 90 degrees, in which you could think then 2 pi over 2 radians would be 180 degrees and 3 pi over 2 would be 270. You would be correct. To show the conversion directly, I'll take 3 pi over 2, which is a measurement in radians, and instead of multiplying by pi over 180, which converts from degrees to radians, I'll multiply by 180 degrees divided by pi radians, using the conversion factor in the other direction. This time, when I do the multiplication, I get 3 times 180 is 540, and that's going to be in degrees. And I'm not going to write the pi because the pi in the numerator will cancel with the pi in the denominator. I will have a 2 in the denominator, and 540 divided by 2 will give me 270 degrees. Notice that I write a unit on my answer this time, where previously I wasn't writing a unit because radians is a unitless measure. For letter B, 4 pi over 5, I will multiply again by 180 degrees over pi. This time I do 4 times 180, which is 720 degrees, and the pi's will cancel. And when I take 720 degrees and divide by 5, I get 144 degrees. Try letter C on your own. Pause the video and see if you can figure out how many degrees are in 9 pi over 10 radians. Did you find that there were 162 degrees in 9 pi over 10 radians? If so, nice work. If not, give it another try before moving on. There are other advantages of radian measure besides the fact that it's a unitless measure of span. We'll see these in the next couple examples. Here, an arc of length 3 pi lies on a circle with radius 4, and we're asked to determine the angle in degrees subtended by the arc. In other words, we know that the radius here is 4, and we know that this arc length, which I've called L here, is 3 pi. And we'd like to know this measure n in degrees. First thing I'll do is I'll find n in radians, because the number of radians of that angle is simply the arc length, 3 pi, divided by 4, the radius. All I need to do now is take that and convert it to degrees. And there are 180 degrees in every pi radians. And thus, this is just a matter of 3 times 180, which is 540, dividing by 4, and getting 135 degrees. As you grow more accustomed with radians, you'll find that you can do many of these conversions, like 3/4 pi from radians to degrees, in your head. One helpful fact is knowing that pi radians is 180 degrees, and thus a quarter pi is 45 degrees. So I can think in terms of quarter pies. How many quarter pies do we need here? We need 3. So 3 45s, and 3 45s is 135 degrees. Another important application of radians comes in physics. When we have an object that's moving in a circular path, we can talk about 2 different speeds for that object. We can talk about its linear speed, which is just a kind of regular speed that we're used to, which is the distance that the object travels divided by the time that it travels. Often we use v for linear speed or velocity. We also have angular speed. Angular speed is defined as the number of radians that are swept out on the central angle divided by the time, because the object is moving in a circle, so it's sweeping out some angle theta on the center there. And if we take that and divide by time, we get its angular speed, which is often signified with the Greek letter here, omega. That fancy W is an omega. Let's take a look at an example of this and see why it's useful. In this example, we have a little mouse that's sitting 10 centimeters from the center of a spinning record. The record's going to spin at 45 rotations per minute, and we're asked to find both the linear speed and the angular speed of this little mouse. So to do this problem, let's start by really analyzing what does 45 rotations per 1 minute really mean. It means every minute the mouse spins around 45 times. It sounds kind of dizzying. And of course, we know that there are 2 pi radians in every 1 rotation, right? And this gives us 90 pi radians per minute. Right? What we just calculated there, just by recognizing that there's 2 pi radians in every 1 rotation, what we've calculated is omega, the angular speed. It means in every minute, 90 pi radians are swept out, right? If we want to switch it to degrees, we could, but we'll find that it's actually more useful to keep angular speed in terms of radians. Because when I go to calculate linear speed, which is v, velocity, this is just a measure of distance divided by time, right? And distance, we know s, that's same as our arc length, right? how far did the mouse actually travel when it spun around the record one time? It spun around, it traveled 2 pi radians. But what was the arc length? Well, you'll see that this is just a matter of taking our 90 pi radians per minute and multiplying by the radius, since s is r theta. And we end up with 900 pi centimeters per minute. And this is a nice thing about radians, besides the fact that they're unitless, or related to the fact that they're unitless, I guess I should say, is we have this nice connection between angular speed and linear speed, which is to say when the mouse is spinning around the record, he's sweeping out a certain number of radians in every spin, but if the record were to stop and the mouse were to go flying, we'd have a quick way to calculate how fast he would move in a straight line. In order to push this conversation about angles forward, we'll need to standardize the way we think about measuring an angle. And the standard way to talk about the angle is in standard position. So we'll put the vertex of the angle at the origin. We'll keep its initial side, which just means one side of the angle, on the positive x-axis. And then the angle, we'll think about measuring it opening in a counterclockwise fashion. Counterclockwise, and it'll just end wherever it ends. And that side is called its terminal side. So a couple important things. We always start on the positive x-axis and always move counterclockwise. Another really important definition for this talk about angles, and eventually for really all of trigonometry, is a definition of the unit circle. The unit circle is simply a circle centered at the origin with a radius of 1. Since we know that every circle has this general form, x minus h squared plus y minus k squared equals radius squared. This is just the general form of a circle with a center at coordinate hk and a radius of r. We can talk about an equation for our unit circle very simply. It would just be x minus 0 squared plus y minus 0 squared equals 1. And as you're about to see, this is really going to be a very useful structure for the study of trigonometry. We'll start our investigation of the unit circle with a little animation here. So here we have a little old man starting at the coordinate 1, 0. And we're going to imagine that he begins walking counterclockwise around the unit circle. And the question of interest to us is whether or not we can pinpoint his exact coordinates at any particular time. And by time, of course, here I mean an angle, right? And the angle will be measured in radians. So let's talk first about some easy coordinates with which we could pinpoint his location. For example, when the little old man here is the leftmost point on the unit circle, we can identify that coordinate there. That's -1, 0. And it's also easy to figure out the angle in standard position. So we're talking about the angle measured like this, right? So this angle right here, well, that's just pi radians. And you can see that right down here. T is equal to 3.1415926. All right, it makes sense that that angle is pi radians, of course, because when we talk about radian measure, it's just S over R. So we're talking about the length of the arc of the semicircle. And the radius, of course, is 1. So it's just 2 pi. Pi over 1. It's also easy to pinpoint some other coordinates for the little man on the unit circle. For example, if I put them right up top here, right about there. Try that again. There we go. The coordinates at this point, of course, and the topmost point on the unit circle are 0, 1, and we're halfway to pi. So the radian measure there is pi over 2. All right. And remember from earlier in the video that pi over 2 is equivalent to 90 degrees. couple more coordinates that are easy to pinpoint here, all the way down on this side, in the lowest part of the unit circle. The coordinates there, of course, are 0, -1, and the radian measure is 3 pi over 2. You can think about measuring this angle in increments of quarter turns on the unit circle: 1 pi over 2, 2 pi over 2, 3 pi over 2. And that brings us to back where we began here. When I bring the little old man back where he started, I could think about this angle that's formed either as an angle of 0 radians and a coordinate of 1, 0, or I could think of it as 2 pi radians because the little old man has taken a full trip around the circle. All right, so those are our first 4 coordinates on the unit circle. Let's get back and derive a few other coordinates. So far, we've seen that we can describe the radian measure and coordinates of these 4 points on the unit circle: 0 radians, pi over 2 radians, pi radians, and 3 pi over 2 radians, and coordinates of 1, 0, 0, 1, -1, 0, and 0, -1. In this last part of the video, we'll find these 4 coordinates and their respective radian measures. For the radian part, it's pretty easy. We just picture our circle divided 8 times rather than simply 4. And notice that this slice right here, these slices right here, divide the first quadrant perfectly in half. And that shows us that the radian measure of this angle, remember measured from standard position, so I'm talking about this angle right here, is half of pi over 2, or pi over 4. If I'd like to know the coordinate for this pi over 4 point, it's relatively simple. I know 2 things about that point. I know it falls on the unit circle, x squared plus y squared equals 1. And I also know that it falls on the line that cuts right through the origin with a slope of 1. So that means it falls on the line y equals x. And so I have a system of equations, 2 equations and 2 unknowns. If I plug x in for y in the first equation, I get x squared plus x squared equals 1, which is to say that 2x squared equals 1, which is to say that x squared is 1/2, or x is equal to plus or minus, and because I'm in the first quadrant, I'll go with plus, the square root of 1/2. So another way to write the square root of 1/2, a more common way, might be square root of 1 over the square root of 2, or when we rationalize, we find that x equals root 2 over 2. And since y equals x, this coordinate right back here, I'll just label it coordinate A, which has a radian measure of pi over 4, will have coordinates root 2 over 2, that's the x coordinate, and then root 2 over 2 again for the y coordinate, since y equals x. Meanwhile, coordinate B over here, which is 3/4 of the way to pi, 3 pi over 4. You think of it as 3 slices of pizza in, will be the same, but with a negative x coordinate, because it's in quadrant 2, where the x's are negative. Meanwhile, this coordinate down here, I'll call it C, which is pi over 4 more than pi, so that's 5 pi over 4, would have the same magnitude of x and y coordinates, but both would be negative. And then lastly, this coordinate d, which is 7 pi over 4, a radian measure of 7 pi over 4, or 315 degrees, like we saw earlier, would have a positive x coordinate and a negative y coordinate. In class, we'll push this a bit further and find the other 8 coordinates on the unit circle. To summarize, the unit circle gives us a framework to begin the study of trigonometry, which is, of course, the study of triangles. And the reason for that is behind every single coordinate on the unit circle, every coordinate can be paired with a radian measure. And behind every coordinate, there's a right triangle hiding, if you look close enough.